Hello and welcome back. Let me open tonight with something you may have watched without knowing what it was. If you're old enough to remember televisions with aerials, you'll remember what happened when you turned to a channel that wasn't broadcasting. The screen filled with static, a shifting field of grey and white speckle, sometimes called snow, accompanied by that flat hissing noise. Most of that was ordinary interference, distant transmitters, electrical equipment, the receiver's own thermal noise. But a small fraction of it, usually quoted at around 1%, was something else entirely. It was light from the beginning of the universe. Radiation released 13.8 billion years ago, when everything that exists was a hot glowing fog, arriving at your aerial after traveling in a straight line ever since, and appearing on your screen as a few flecks of snow among the rest. People sat in front of that for decades, waiting for a program to start, watching the afterglow of the origin of everything without the faintest idea. And it's still arriving. Right now as you lie there, that same radiation is passing through the roof, through the ceiling, through the blanket, and through you. Something like 400 million photons per cubic meter of space, everywhere, in every direction. Most pass straight through without interacting at all, but a fraction land on you. And every one of those has been traveling, undisturbed, for 13.8 billion years, since before there were stars or galaxies or atoms heavier than helium, and you are the first thing it has touched. Let's define it properly, because the name is accurate, but not very illuminating. The cosmic microwave background is a bath of radiation that fills all of space, arriving from every direction at a temperature of about 2.7 degrees above absolute zero. It's not coming from anywhere in particular. There's no source you could point to, no object, no region, no direction where it's stronger. It's simply everywhere, uniform to an extraordinary degree, filling the entire universe. And it's old. It was released when the universe was about 380,000 years old, which sounds like a long time until you set it against 13.8 billion. As a fraction, it's roughly the first 3 hours of a 100-year life. At the moment of release, it was visible light, a bright orange glow, filling everything. It has been stretched by the expansion of the universe ever since, by a factor of about 1100, which has shifted it down through infrared and into the microwave range and cooled it correspondingly. So it's the same light, still traveling, just enormously stretched. And because it comes from a specific moment, it's effectively a photograph, the earliest image of the universe that will ever be obtainable by any means we currently understand. Everything we know about the composition, age, geometry, and history of the cosmos comes substantially from studying it. It is, without much competition, the most information-rich observation in astronomy. To understand where it came from, we need to go back to what the universe was like before it was released. In the first few 100,000 years, everything was hot and dense. Not hot like a fire, hot like the inside of a star, and then hotter as you go further back, and dense enough that matter and radiation were thoroughly mixed together. At those temperatures, atoms could not exist. Any electron that tried to settle into orbit around a nucleus was immediately knocked free again by a passing photon. So the universe was a plasma, bare atomic nuclei, mostly single protons with some helium, and free electrons moving independently. And a plasma is opaque. Free electrons scatter light extremely effectively. A photon traveling through cannot get far before running into one and being deflected in a random new direction. So light existed in enormous quantities, and it went nowhere. Every photon was constantly absorbed and re-emitted and deflected, bouncing around in place, unable to travel any meaningful distance. The whole universe was in that condition, everywhere, at once. Bright, blindingly so, and completely opaque. You could not have seen more than a very short distance in any direction, because the light reaching your eye would have been scattered from just nearby, carrying no information about anything further away. The usual comparison is the inside of a cloud, or the interior of the sun, filled with light and impossible to see through. Then the universe expanded, and expansion cools things. The mechanism for radiation is straightforward. As space stretches, the wavelengths of the light traveling through it stretch too. Longer wavelength means lower energy per photon, which means a lower temperature. So the whole system cooled steadily, from unimaginable temperatures in the first instance, down through millions of degrees, down toward thousands. And at a temperature of around 3000 degrees, something changed. That's cool enough for electrons to be captured by nuclei and stay captured, because the passing photons no longer have enough energy to knock them free. Electrons settled into orbits. Neutral atoms formed for the first time, hydrogen mostly, along with helium. The process is called recombination, which is a slightly odd name, since the electrons and nuclei had never been combined before. The term is a historical artifact from laboratory plasma physics, and it stuck. And it wasn't instantaneous. It took several tens of thousands of years for the transition to complete, which matters for the details. But the bulk of it happened within a comparatively short window, around 380,000 years after the beginning. The consequence was immediate and total. With the electrons bound into atoms, there was nothing left to scatter the light. Neutral hydrogen is transparent to most wavelengths. Free electrons are not. The moment the electrons were captured, the universe became clear. And all that trapped radiation, which had been bouncing in place since the beginning, was suddenly free to travel. It set off in every direction, in straight lines, and it has been traveling ever since. That's the cosmic microwave background. The light that was released at the instant the universe became transparent, still in flight, still arriving. There's a useful way to think about what we see. Look in any direction, far enough, and you're looking back in time, because light takes time to arrive. Keep looking further, and eventually you reach the distance at which the light has been traveling since that moment of transparency. Beyond that, you cannot see. Not because there's nothing there, but because the universe was opaque, and no light from earlier can reach us. That boundary is called the surface of last scattering, and it surrounds us in every direction at the same distance, like the inner wall of an enormous sphere. It isn't a real surface. There's nothing physically there. It's simply the set of points from which light released at that moment is arriving here, now. And it's different for every observer, and it moves outward as time passes. That last point deserves a chapter, because it clears up the most common confusion about this subject. The surface of last scattering is not a place. It's a distance. The distance from which light emitted at that moment happens to be reaching you at this instant. Which means every observer in the universe has their own centered on themselves. An astronomer in a galaxy, 1 billion light years away, has a sphere of last scattering centered on their position, overlapping ours substantially, but extending further in one direction and falling short in the other. And the material we see as our last scattering surface is not special either. It's ordinary matter, hydrogen and helium, which by now has long since formed into stars and galaxies. Somewhere out there at that distance, a galaxy's full of stars, going about their business, entirely unaware. If we could look at them as they are now, we'd see an ordinary region of the universe. What we actually see is the light they emitted when they were an undifferentiated glowing fog 13.8 billion years ago, because that's the light that has had time to reach us. The surface also moves. Every year, light from slightly further away arrives, so the sphere expands. It's not a boundary of the universe, it's a boundary of what has had time to reach us. And in the far future, it becomes invisible entirely, stretched by the continuing expansion until no instrument could detect it. But we'll come to that much later. Let's talk about the temperature, because it's one of the most precisely known numbers in astronomy. The cosmic microwave background has a temperature of 2.725 degrees above absolute zero. That's minus 270.4 degrees Celsius. Very cold, but not nothing. It's also, in a real sense, the temperature of the universe. Any object in deep space far from any star will eventually settle to roughly that temperature, because that's the radiation bath it's sitting in. It cannot cool below it by radiating, because it's receiving as much as it emits. which means the coldest anything can passively get, anywhere in the universe, is 2.7 degrees. Unless you do something active to cool it, or unless it's expanding rapidly enough to cool by expansion. That temperature has been falling for the entire history of the universe. When the light was released, it corresponded to about 3,000 degrees. Expansion has stretched it by a factor of about 1100 since, and temperature falls in the same proportion, giving the 2.7 we measure. There was therefore a period when the universe was every temperature in between. There was a time when the ambient temperature everywhere was that of boiling water, and a time, a few million years in, when it was comfortable room temperature, everywhere, in every direction, with nothing at all present to enjoy it. And it continues to fall. In 100 billion years, it will be a small fraction of a degree, and in a trillion, less still, approaching absolute zero forever without arriving. There's a property of this radiation that's worth a chapter of its own, because it's one of the most striking measurements in the history of physics. When any object is in thermal equilibrium, when its parts have had time to share energy thoroughly, it emits radiation with a very specific distribution of wavelengths. Lots at some middle wavelength, tailing off in both directions, in a shape determined entirely by the temperature and nothing else. That's called a blackbody spectrum, and it's ubiquitous. Stars approximate it, hot metal approximates it, your own body radiates it in the infrared. The theory of it was one of the founding problems of quantum mechanics. Classical physics predicted an absurdity: infinite energy at short wavelengths, and Max Planck solved it in 1900 by proposing that energy comes in discrete packets, which was the beginning of quantum theory. Now, the cosmic microwave background should be a perfect blackbody, because it was released from a system in thorough equilibrium, everything scattering off everything, endlessly, for hundreds of thousands of years. And when it was measured properly by a satellite in 1990, it turned out to be a blackbody to an extraordinary degree. The measured points fit the theoretical curves so closely that the error bars are smaller than the thickness of the line on any graph you'd draw. It is the most perfect blackbody spectrum ever observed, anywhere, including in laboratories. Nothing anyone has built comes close. When the result was first shown at a conference in 1990, the audience gave it a standing ovation, which is not something that ordinarily happens for a graph. Now let's do the discovery, because it's one of the great accidents in science. In 1964, two radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were preparing to use a large horn-shaped antenna for radio astronomy. It had been built for satellite communications and was no longer needed for that. Before they could measure anything faint, they needed to characterize the noise in the system, so they pointed it at empty sky and measured what came in. There was more than there should have been. A persistent hiss corresponding to a temperature of about 3 degrees above absolute zero, which they could not account for. They checked everything. They considered radiation from the Milky Way, from the atmosphere, from nearby New York City. They dismantled and rebuilt parts of the receiver. They checked for interference from the antenna's own structure. The signal was the same in every direction they pointed, at every time of day, in every season, which ruled out essentially every terrestrial and local astronomical source, since all of those would vary as the sky moved overhead. And it wouldn't go away. The most famous detail of that investigation deserves its own chapter, because it's exactly the sort of thing that actually happens. A pair of pigeons had taken up residence inside the horn antenna, and they had left a substantial deposit inside it, which Penzias later described in a phrase that has followed him ever since, as a white dielectric material. Bird droppings might plausibly have absorbed and re-radiated energy, contributing noise, so it had to be eliminated. They trapped the pigeons and sent them to a Bell Labs site some distance away. The pigeons, being homing pigeons, came back. They then cleaned the antenna thoroughly, scrubbing out the interior. And the signal was unchanged. Exactly the same excess temperature in every direction after the birds and their contribution had been removed. That process, the checking, the cleaning, the elimination of every mundane explanation, took the better part of a year. And it's the reason the result was believed when it was published. They had ruled out everything else first. While that was happening, a group at Princeton, about an hour's drive from the antenna, was building an instrument to look for exactly this signal. Robert Dicker had reasoned that if the universe had a hot, dense early phase, there should be leftover radiation, cooled by expansion into the microwave range. He set his colleagues Peter Roll and David Wilkinson to build a detector, and Jim Peebles to work out the theory. Then Penzias, discussing his puzzling noise with another astronomer, was told about the Princeton work and given Dickie's number. He called. Dickie listened, hung up, turned to his colleagues and said, by several accounts, "Boys, we've been scooped." The two groups met, compared notes, and agreed to publish simultaneously 2 papers in the same issue of the same journal in 1965. Penzias and Wilson reported the measurement, carefully describing it only as an excess antenna temperature. The Princeton group's paper explained what it meant. There's something admirable in that arrangement. One group had spent a year eliminating pigeons. The other had built a theory and was weeks from measuring it themselves. They shared the moment rather than racing. Penzias and Wilson received the Nobel Prize in 1978. Dickie did not, which has been remarked upon ever since. The strangest part of the story is that the prediction already existed and had been ignored for 17 years. In the 1940s, George Gamow was working out what happens to matter in a hot early universe, how the light elements might have been forged in the first minutes. 2 of his collaborators, Ralph Alpha and Robert Herman, followed the reasoning through to its consequence. If the universe was hot and dense and full of radiation, and if it then expanded and cooled, that radiation would still be present today, stretched to long wavelengths. They published an estimate in 1948, about 5 degrees above absolute zero, remarkably close to the true value, from first principles, 17 years before anyone found it. And then essentially nothing happened. The prediction was not followed up. No one attempted the measurement, and it drifted out of general awareness. Several reasons have been suggested. The technology to detect such a signal was marginal at the time. The prediction was buried in papers about element formation rather than presented as a target, and the idea of a hot beginning was not widely accepted. So by 1964, the people building detectors at Princeton were rediscovering an idea that had been in the literature since before some of them started their doctorates. Alpha and Herman were, understandably, frustrated by this for the rest of their lives, and made the point repeatedly and with justification. There's a stranger footnote from 1941, when nobody was looking for anything of the kind. An astronomer named Andrew McKellar was studying the spectra of stars and noticed absorption lines from cyanogen molecules, a simple carbon-nitrogen compound, in the interstellar gas along the line of sight. The relative strengths of those lines depend on the temperature of the molecule's surroundings, because the ratio between molecules in different rotational states is set by the ambient radiation. From the observed ratio, he calculated an effective temperature of about 2.3 degrees above absolute zero. He published it. It was a measurement of the temperature of interstellar space, and nobody knew what to make of it, and it sat in the literature unexplained for 24 years. It was, in fact, a measurement of the cosmic microwave background, made by watching how molecules in space were being warmed by it, more than 2 decades before anyone knew what it was. That method still works, incidentally, and it's useful, because you can observe such molecules in distant galaxies. You can measure the temperature of the microwave background at earlier epochs, and check that it was hotter in the past by exactly the predicted amount. It was. The discovery ended an argument that had been running for 2 decades, and it's worth a chapter on what was at stake. There were 2 competing pictures of the universe. One held that it began in a hot, dense state and has been expanding and cooling ever since. The other held that it expands forever, but that new matter is continuously created in the gaps, so that it looks the same at all times and had no beginning. The second was called the steady-state model. and it was defended by serious and capable people, Fred Hoyle among them, partly on the grounds that a universe with a beginning raised uncomfortable questions. Hoyle, incidentally, coined the phrase Big Bang on the radio in 1949. Accounts differ on whether he meant it dismissively. He later said he was reaching for a vivid image. Either way, it stuck, and it's a poor name that encourages exactly the wrong mental picture of an explosion in space. A steady universe has no reason to be filled with faint microwave radiation at a specific temperature with a perfect thermal spectrum. There's nothing in the model to produce it. A universe with a hot beginning predicts it necessarily. So the 1965 measurement was decisive in a way that few single observations are. Within a few years, the steady-state model had essentially no adherents left, and the hot beginning became the standard picture. Hoyle continued to defend variance of his position for the rest of his life, which is its own kind of admirable, and he was substantially right about several other things, including where the elements come from. Once the background was established, the next question was whether it was perfectly smooth, and for 27 years, every attempt to find variation came back empty, which was becoming a problem. Here's why it mattered. The universe today is extremely lumpy. Galaxies, clusters, filaments, voids. All of that structure grew from slight density variations amplified by gravity. So the early universe must have had those variations, and they should appear in the microwave background as slight differences in temperature from place to place, because denser regions would have been slightly different in temperature when the light was released. But measurement after measurement found nothing. The sky was the same temperature in every direction, to a part in 1,000, then a part in 10,000, and still nothing. Which raised an awkward possibility. If the initial variations were too small, gravity would not have had time to build the structure we see, and something in the picture must be wrong. The other complication is that the sky isn't clean. Our own galaxy emits radiation at these wavelengths, from dust and from electrons spiraling in magnetic fields, far more strongly than the tiny variations being sought. So the foreground has to be modeled and removed. And there was one variation that everybody found immediately, and it turned out to be about us rather than about the universe. That variation is called the dipole, and it's by far the largest feature in the microwave sky. One half of the sky is slightly warmer than average, and the opposite half slightly cooler, by a few thousandths of a degree, in a smooth gradient with one hot pole and one cold. It's a Doppler effect. We're moving through the radiation, so it's slightly blue shifted ahead of us and red shifted behind, and blue shifted light corresponds to a slightly higher temperature. It was detected in the 1970s using instruments flown on high-altitude aircraft, and it's now measured to great precision. From it, our velocity can be extracted, about 370 kilometers per second, in the direction of the constellation Leo. That's the Sun's motion, and subtracting the Sun's orbit around the galaxy and the galaxy's motion within the local group leaves about 630 kilometers per second for our whole local collection of galaxies. So the largest feature in the oldest light in the universe is not about the universe at all. It's about the motion of the observer. It has to be measured and removed before anything else can be studied, and once it is, the sky is uniform to about 1 part in 100,000, and the real variations are underneath. In November 1989, a NASA satellite called COBE was launched, carrying 3 instruments, and it changed cosmology twice. The first results came quickly. One instrument measured the spectrum, the distribution of wavelengths, with unprecedented precision, comparing the sky against an internal reference blackbody carried on board. The result, presented in January 1990, was the perfect curve we discussed earlier. The measured points fell on the theoretical blackbody so exactly that the uncertainties were invisible on the plot. That alone confirmed the hot beginning beyond serious dispute, because nothing else produces a spectrum that clean. The second result took 2 more years of data and analysis. Another instrument compared the temperature of different patches of sky against each other very precisely over the whole sky. And in April 1992, the team announced that they had found the variations. Faint mottling, patches warmer and cooler than average by about 1 part in 100,000, spread across the sky in a pattern consistent with what the theory required. The announcement was accompanied by a certain amount of overstatement in the press, including a much-quoted remark about seeing the face of God, which the scientists involved spent years qualifying. But the underlying result was real, and it was what everyone had been waiting for since the 1960s. The seeds were there. Let's spend a chapter on what those variations actually represent, because it's subtler than it first appears. A warmer patch does not simply mean hotter material. Several effects contribute. Denser regions were slightly hotter intrinsically, because compressing a gas heats it. But light escaping from a denser region also has to climb out of a deeper gravitational well, which costs it energy and makes it appear cooler. Those two effects partly cancel, and which wins depends on the scale being considered. For the largest patches, the gravitational effect dominates, and denser regions appear cooler. There's a third contribution. The material was moving, falling into or out of the density variations, which produces Doppler shifts. So the pattern is a combination of density, gravitational potential, and motion, all frozen at the moment of release, and disentangling them requires the full theory. But the essential point is simple. The variations trace the density fluctuations that existed at 380,000 years, and those are the seeds from which every galaxy in the universe subsequently grew. Which means the mottled pattern is, quite literally, a map of where things would eventually be. Look at a warm or cool patch, and you're looking at the ancestor of a supercluster or a void. The obvious next question is what produced those variations, and the leading answer traces them to the first fraction of the first second. The theory is inflation, a brief episode of enormously rapid expansion in the earliest instant, during which the universe doubled in size, perhaps 80 or 90 times over, in a span of time written with more than 30 zeros after the decimal point. It was proposed in 1980 to solve several unrelated problems. Why the universe is so uniform, why space is so flat, why certain predicted exotic particles are absent. And it had a consequence nobody was looking for. In quantum theory, no field can be perfectly still. There's always an irreducible jitter, which normally matters only at subatomic scales. But if space itself is being stretched enormously and rapidly, those fluctuations get stretched with it, blown up from subatomic size to scales larger than the observable universe, and frozen in place as slight variations in density. So the pattern of warm and cool patches would be quantum uncertainty, magnified beyond recognition, preserved as a permanent map. And the theory doesn't just predict that variations exist, it predicts their statistical character, how their sizes should be distributed, roughly equally on all scales, with a very slight tilt in a specific direction. When the measurements were made precisely enough, the pattern matched, including the tilt. Now we come to the most beautiful part of this subject, and it's worth taking slowly. In that hot early plasma, matter was not spread perfectly evenly. There were regions slightly denser than average, and gravity pulled more material into them. But the ordinary matter was tangled up with radiation, and radiation pushes. As material fell into a dense region, the pressure of the light trapped with it built up and shoved outward. The region overshot, bounced, and fell in again. In and out, over and over, across the whole universe at once. Those are pressure waves traveling through a medium, which is to say, they were sound waves, real sound, propagating through the plasma at more than half the speed of light, at frequencies far too low for any ear. The universe rang like a struck bell for hundreds of thousands of years. And then the fog cleared, and the light escaped, and the ringing stopped instantly, because it was the light that had been providing the pressure. Everything froze mid-oscillation. So the warm and cool patches we see are the last frame of that ringing. Regions caught at maximum compression, regions caught at maximum rarefaction, and every stage in between, depending on the size of the region and how many oscillations it had time to complete before the music stopped. That freeze frame is what makes the microwave background so informative, and the analysis is elegant. A region of a particular size has a particular oscillation period. Regions that had just completed exactly half an oscillation when the light escaped were caught at maximum compression, and those appear at a specific angular size on the sky. Regions half that size had time for a full oscillation, and are caught at maximum rarefaction, appearing at a smaller angular scale. And so on, alternating, producing a series of preferred scales in the pattern. So astronomers measure how much variation there is at each angular scale across the sky, and plot the result. What emerges is a curve with a series of peaks, the acoustic peaks, at the scales corresponding to those preferred oscillations. That plot is called the power spectrum, and it is the single most important object in modern cosmology. Nearly everything we claim to know about the universe's contents and geometry is extracted from the positions and heights of those peaks. It's essentially the same reasoning that lets you deduce the size and shape of a musical instrument from the sound it makes. The universe made a sound. We have a recording of the final instant, and from its harmonic content, we can work out the properties of the instrument. Let's go through what the peaks tell us, one at a time, because each carries something different. The first peak is the largest and most prominent, and its position on the sky measures the geometry of space. Here's the reasoning. Physics tells us the true physical size of the regions that produce that peak. It's set by how far a sound wave could travel in the plasma before the light escaped, which is calculable. We also measure the angle those regions subtend on our sky. Knowing a true size and an apparent angle gives you the geometry of the space in between. In flat space, ordinary geometry applies. In positively curved space, distant objects appear larger than they should. In negatively curved space, smaller. The measurements say the universe is flat, to within a fraction of a percent. Parallel lines stay parallel across billions of light years. That was established convincingly around 2000 by balloon-borne experiments flown over Antarctica, and confirmed with far greater precision since. And flatness has a consequence. In general relativity, it requires a specific total energy density in the universe, the critical density exactly, which immediately created a problem, because the matter we could account for came to only about a third of that. The subsequent peaks carry different information, and this is where the composition of the universe emerges. The relative heights of the odd and even peaks are sensitive to how much ordinary matter there is. Ordinary matter, protons and neutrons, feels the radiation pressure, so more of it means the compressions are enhanced relative to the rarefactions, which raises the odd peaks compared to the even ones. Measure that as symmetry, and you get the density of ordinary matter directly. The answer comes out at about 5% of the critical density. And remarkably, that agrees with a completely independent measurement, the abundances of light elements produced in the first few minutes, which also depends sensitively on how densely packed the protons and neutrons were. Two entirely different physical arguments, from eras separated by 380,000 years, giving the same number. The third peak is sensitive to dark matter. Because dark matter doesn't interact with radiation, it never bounced. It simply kept falling inward, deepening the gravitational wells while the ordinary matter was still oscillating. That changes the pattern in a calculable way, and measuring it gives the dark matter density, about 27%. 5 plus 27 is 32, and the geometry demands 100, which leaves 68% unaccounted for. And that's how the microwave background independently confirms dark energy, without any reference to supernovae. What emerges from all of this is a model of remarkable economy, and it's worth stating plainly. The standard cosmological model describes the entire observable universe, its contents, geometry, expansion history, and the statistical properties of all its structure, using 6 free parameters. They are, roughly, the density of ordinary matter, the density of dark matter, the age or equivalently the expansion rate, the amplitude of the primordial fluctuations, how that amplitude varies with scale, and a number describing when the first stars reionize the gas. 6 numbers. Fitted to the power spectrum and to nothing else, they reproduce the entire observed pattern across the whole sky at every angular scale. Thousands of independent data points, matched by a 6-parameter curve. And the same 6 numbers then predict, without further adjustment, the observed distribution of galaxies, the abundances of light elements, the pattern of gravitational lensing, and the growth of structure over time. That's an extraordinary situation. It's the reason cosmology is described as having become a precision science, and it happened within about 25 years. It doesn't mean we understand what those numbers mean. 2 of them describe substances nobody can identify. But the description is tight, and it works, and it's the same everywhere. Let's state the outputs slowly, because they're the headline results of modern cosmology. The age of the universe, 13.8 billion years, known to better than 1%. That's an extraordinary thing to be able to say. The composition, about 5% ordinary matter, 27% dark matter, 68% dark energy. Everything anyone has ever seen or touched is the 5%. The geometry, flat, to within a fraction of a percent. The primordial fluctuations, an amplitude of about 1 part in 100,000, distributed almost equally across scales, with a slight tilt toward more power on larger scales, exactly as inflation predicts, and measured precisely enough that the tilt is now established at high significance. The reionization epoch. The first stars ionized the intergalactic gas somewhere around a few 100 million years after the beginning, based on the fraction of microwave photons that were scattered by the free electrons they produced. And the expansion rate, around 67 or 68 kilometers per second per megaparsec, which is where the current disagreement lies, since local measurements give a value about 10% higher, and the discrepancy has not gone away. Let's spend a chapter on the instruments, because each generation improved the picture substantially. COBE, launched in 1989, made the first detection of the variations. Its resolution was about 7 degrees, meaning it could distinguish patches roughly 14 times the width of the full moon. It could see that variations existed, but not their detailed structure. WMAP, launched in 2001, improved that to about 1/3 of a degree, and maps the whole sky for 9 years. That resolution was enough to measure the first several acoustic peaks properly, and its results established the 6-parameter model as the standard picture. Planck, launched in 2009, improved it further, to about 5 arc minutes, roughly 1/6 of the moon's width, across 9 frequency bands. That frequency coverage was crucial, because it allowed the foreground emission from our own galaxy to be identified and separated far more effectively. Planck's final results, released through the 2010s, remain the definitive full-sky measurements. It measured the temperature pattern essentially, as well as it can be measured. The remaining uncertainty at large scales comes not from instruments, but from the fact that we have only one sky to look at. Ground-based and balloon experiments have contributed enormously alongside them, particularly at small angular scales, and for polarization, from sites in Antarctica and the Atacama Desert, where the air is exceptionally dry. That last point deserves a chapter, because it's a genuine and permanent limitation. Ordinarily, if a measurement is uncertain, you take more data. But for the largest angular scales in the microwave background, there is no more data to take. The reason is that there are only so many independent large patches on a sphere. At the very largest scales, you can fit only a handful of independent regions across the whole sky. So the statistics are inherently limited, no matter how good your instrument. That's called cosmic variance, and it sets a floor on the precision achievable at large scales. Planck reached it. No future instrument will do better on the temperature pattern at those scales, because the limitation isn't technological. It's an unusual position for an experimental science, a known, permanent, irreducible uncertainty, arising from having exactly one universe available for study. The consequence is that the largest scale features, including some of the anomalies we'll come to, can never be measured more precisely. If a feature looks slightly unusual at those scales, we will never know whether it's a genuine oddity or simply what one sky happens to look like. Which is worth holding at this hour. Some questions in this field don't have more data coming. The answer is what it is, and the uncertainty is permanent. There's more information in this radiation than temperature alone, and the second layer has occupied the field for 2 decades. Light can be polarized, meaning the electric field oscillates preferentially in one direction rather than randomly. And the microwave background is slightly polarized at the level of a few percent because of how it scattered off electrons in the final moments before release. Scattering imparts polarization when the radiation arriving at an electron is not perfectly uniform from all directions, which it wasn't because of the density variations. So the polarization pattern carries information about the motions of the plasma at the moment of last scattering, complementing what the temperature pattern says about density. That pattern can be decomposed into 2 mathematically distinct kinds. One, called east modes, has a pattern that looks like radial or circular arrangements around hot and cold spots. Those are produced by ordinary density variations, and they've been measured in detail, first detected in 2002, and now mapped precisely. The other, called B modes, has a swirling, handed pattern that density variations alone cannot produce. And that's the prize. Because one thing that could produce B modes at large angular scales is gravitational waves from inflation itself, ripples in spacetime generated in the first fraction of the first second. That search produced one of the most instructive episodes in modern science, and it deserves a careful chapter. In March 2014, a collaboration operating a telescope at the South Pole called a press conference and announced they had detected the primordial B-mode signal, evidence of gravitational waves from inflation. It would have been among the most important results in the history of cosmology. There was video of a team member arriving at Andrei Lin's house to tell him that his life's work had been confirmed, and his reaction went around the world. Within months it came apart. The signal was real, but the interpretation wasn't. Dust in our own galaxy, grains aligned by magnetic fields, produces a polarization pattern that can mimic the primordial one, and the amount of foreground dust in that patch of sky had been underestimated. When a European satellite released better dust maps, the excess could be accounted for almost entirely by material a few hundred light years away. The collaboration retracted the claim, and the joint reanalysis was done in cooperation with the team whose data had undermined the result. Everyone involved behaved honorably, but it was a difficult public episode. And it changed how the field handles announcements. It's now standard to have foreground modeling settled before claiming a detection, and to publish through peer review rather than press conference. The search continues, with better instruments and much better dust maps. And the limits keep tightening. Let's spend a chapter on why so much effort goes into this, because the stakes are unusual. If inflation happened, it would have produced gravitational waves, ripples in spacetime generated by quantum fluctuations in the geometry itself, stretched to enormous scales by the same expansion that stretched the density fluctuations. Those waves would still be present, and they would have imprinted a specific swirling polarization pattern on the microwave background at large angular scales. Detecting them would do 2 things. It would confirm inflation far more strongly than the current evidence does, and it would measure the energy scale at which it occurred, which is far beyond anything any accelerator could reach, and would be a direct probe of physics at energies we can access in no other way. It would also be the first evidence of a purely quantum gravitational effect, gravitational waves generated by quantum fluctuations of spacetime, which is the only place those 2 frameworks currently touch observably. The amplitude is characterized by a number, and the limits on it have been driven down steadily by successive experiments. Some versions of inflation are already excluded. Others predict signals below current sensitivity. Instruments now operating and being built in Antarctica, in the Atacama, and a satellite in preparation should improve the limits by another order of magnitude within a decade or so. Either they find it, which would be historic, or they push the limits low enough to exclude the simplest models, which would also be significant. There are several ways the microwave background gets modified on its journey here, and each carries additional information. Let's take them in turn. The first is the Sachs-Wolf effect. Light emitted from a region with a deeper gravitational well has to climb out, which costs it energy, making it appear cooler. That's the dominant contribution to the temperature variations at the largest angular scales. The second is a version of the same thing operating during the journey. As a photon crosses a large structure, a cluster or a void, it falls in, gaining energy, and climbs out, losing it. In a static universe, those cancel exactly. But if the structure changes while the photon is crossing, they don't cancel. And in a universe where dark energy is pulling structures apart, gravitational wells become shallower over time. So a photon climbs out of a shallower well than it fell into, and emerges slightly warmer. That's the integrated Sachs-Wolf effect, and it predicts a specific correlation. The microwave background should be very slightly warmer in directions where there are great concentrations of galaxies, and cooler toward great voids. Astronomers cross-correlated microwave maps with catalogues of millions of galaxies and found exactly that correlation at the predicted size, which is an independent piece of evidence for dark energy, because in a universe without it, the effect vanishes. The second modification happens when the light passes through a galaxy cluster. Clusters are filled with gas at tens of millions of degrees, thin but enormous in extent, and full of fast-moving electrons. When microwave photons pass through, some collide with those electrons and gain energy. That shifts the spectrum slightly. Fewer low-energy photons, more high-energy ones, in a precisely predictable pattern. The result is that a cluster leaves an imprint on the microwave sky, appearing as a small cool spot at low frequencies and a warm one at high frequencies. It's called the Sunyaev-Zeldovich effect, after the two Soviet physicists who worked it out in the late 1960s. And it has a remarkable property. The size of the effect doesn't depend on how far away the cluster is. Ordinary brightness falls off with the square of distance, but this depends only on how much hot gas the light passed through. So a distant cluster produces the same imprint as a nearby one, which makes it an ideal way to find clusters anywhere, at any distance, including behind the dust of our own galaxy. Surveys using the method have catalogued thousands. So the oldest light in the universe has been turned into a tool for finding the largest structures in it, by measuring how they nudge it in passing. The third modification is gravitational lensing, and it turns the microwave background into a map of everything between us and it. Light traveling from the last scattering surface passes through all the structure in the universe, every cluster, every filament, every void, and mass bends light. So the pattern we observe is not the pattern that was emitted. It's been subtly distorted, with hot and cold patches displaced by small amounts, in a way that depends on the mass distribution along each line of sight. The displacements are tiny, a few arc minutes, but they're statistically detectable, because they produce specific correlations in the observed pattern that wouldn't otherwise be there. And by measuring those correlations, astronomers can reconstruct a map of all the mass in the universe, projected along every direction, including dark matter, since gravity responds to everything. That's been done, first tentatively around 2011, and now routinely and precisely. There are now full sky maps of the projected mass distribution, derived entirely from how the oldest light was bent on its way here. It also lets the growth of structure be measured, which constrains dark energy and tests general relativity on the largest scales. So the microwave background does double duty, a photograph of the beginning and a backlight illuminating everything that has happened since. Before any of that analysis can happen, there's a substantial obstacle, and it's our own galaxy. The Milky Way emits at microwave wavelengths and far more brightly than the variations being sought. There are several separate sources. Dust grains, warmed by starlight, radiate in the far infrared and into the microwave range. Electrons spiraling in magnetic fields produce synchrotron radiation, strongest at lower frequencies. ionized gas produces free emission, and there's an additional component thought to come from small spinning dust grains, which was only identified in the 1990s. Each of those has a different dependence on frequency, and that's the key to removing them. If you observe the sky at many different frequencies, you can separate the components, because the cosmic background has a blackbody spectrum with a known shape, while each foreground has its own distinct signature. That's why the satellites carried multiple frequency bands. Planck observed at 9, spanning a wide range, specifically to make this separation possible. The techniques are sophisticated, and several independent methods are applied to the same data as a cross-check. The resulting cleaned maps agree well with each other, which is one reason the results are trusted. But near the galactic plane, the foreground is simply too strong to remove reliably, so a band across the middle of every map is masked out, typically 20% or so of the sky, excluded from the analysis entirely. Let's spend a chapter on the famous image, because it's worth knowing how to read it. You've almost certainly seen it, an oval, filled with a mottled pattern of blue and red and yellow speckles, presented as a map of the early universe. The oval is the whole sky, flattened onto a page, the same kind of projection used for world maps, chosen to preserve areas so that a region's size on the map matches its true share of the sky. The mottling is the temperature variation after the dipole has been removed and the galactic foreground subtracted. The colors are not real, they're a scale, with red typically indicating slightly warmer regions and blue slightly cooler. And the scale is the crucial thing to understand. The full range from the reddest to the bluest is about 400 millionths of a degree. If the colors were scaled to represent absolute temperature, the entire map would be a single uniform shade with no visible structure at all. So the dramatic mottling is an enormous exaggeration of a very subtle effect. The sky really is smoothed to 1 part in 100,000. The image amplifies the departures by a factor of tens of thousands to make them visible. Which is worth knowing, because the image gives an impression of a lumpy, chaotic early universe, and the reality is almost perfect uniformity, with the faintest possible texture on top. There are a few features in the map that have attracted attention as possible anomalies, and the most famous deserves a chapter. In the southern sky, there's a region noticeably cooler than average and larger than the typical patch, a broad, cool area spanning several degrees. It's known as the cold spot, and it's been discussed since the early 2000s. It's not dramatic in absolute terms. The temperature difference is around 70 millionths of a degree against a background that varies by 100 or so. The question is whether a feature that large and that cool should turn up by chance. Several explanations have been proposed. The simplest is chance. In any random field, some region will be the coldest, and human pattern recognition is very good at finding it and then being impressed. Another is a foreground effect. An enormous void along that line of sight would cool passing light slightly through the integrated Sachs-Wolf effect we discussed. Surveys have found an underdense region in roughly that direction, though whether it's sufficient is disputed. And a third, more speculative, is that it's the imprint of a collision with another bubble universe in the first moments, a proposal that has been made in the literature and taken seriously enough to be tested. The current state is unsettled but unexciting. Most cosmologists consider chance plus foreground effects the likely explanation, and the statistical significance has softened as the analysis has improved. There are a few other reported peculiarities, and they cluster at the largest angular scales, which is where cosmic variance bites hardest. One is that the amount of variation at the very largest scales, what's called the quadrupole, appears somewhat lower than the standard model predicts. That was noticed by Kobe and persisted in later data. Another is that some of the largest scale patterns appear to align with each other, and with the plane of our own solar system, in a way that has no obvious reason. That was given the memorable nickname, the axis of evil, which has done more for its fame than the evidence has. A third is a reported asymmetry, slightly more variation in one hemisphere of the sky than the other. All of these are at the level where the significance is difficult to assess, and all suffer from the same problem. They were noticed after looking at the data. If you examine a map for unusual features, you will find some, and calculating how surprising they are afterwards is notoriously slippery. They're also at scales where cosmic variance means no better measurement is possible. We will never have more data on the largest patches. So the honest position is that these are curiosities of uncertain significance, taken moderately seriously, unlikely to be resolved, and not currently regarded as evidence against the standard model by most of the field. There's one tension that is taken very seriously indeed, and it involves the microwave background directly. The expansion rate of the universe can be measured two ways. Locally, build a ladder of distance measurements from nearby stars outward, measure how fast galaxies recede at known distances, and extract the rate. Or indirectly, fit the standard model to the microwave background power spectrum and let the model tell you what the expansion rate must be today. The two disagree. The local measurements give a value around 10% higher than the microwave prediction. Both have become extremely precise over the past decade, and the gap is now far larger than either side's stated uncertainty. And crucially, the disagreement has hardened as measurements improved, which is the opposite of what usually happens with a systematic error. Enormous effort has gone into checking both sides. The distance ladder has been rebuilt using different rungs, different kinds of stars, different calibrations, entirely independent methods. The microwave analysis has been scrutinized by multiple teams. It hasn't gone away. Possible resolutions include an unrecognized systematic somewhere, or new physics in the early universe, some additional component that changes the relationship between what the microwave background shows and what the expansion rate is today. It's currently the most prominent open problem in cosmology, and the microwave background sits at the center of it. There's a second, milder disagreement worth a chapter, because it involves the growth of structure. The microwave background tells us how lumpy the universe was at 380,000 years. The standard model then predicts how much that lumpiness should have grown by today, under gravity. That prediction can be checked by measuring how clustered galaxies are now, and by measuring gravitational lensing in surveys of galaxy shapes. And some of those measurements come out slightly lower than the microwave prediction. The universe appears a little less clumpy today than the early conditions plus standard gravity would suggest. The discrepancy is modest, a few percent, at a significance level where people are interested but not alarmed, and different surveys give somewhat different answers. If it's real, it might indicate something about dark energy, or about how much neutrinos have suppressed structure growth, or about modifications to gravity. If it's not, it's a systematic in how galaxy shapes are measured, or how the relationship between galaxies and mass is modeled, both of which are genuinely difficult. Recent results have gone in both directions, with some analyses easing the tension and others maintaining it. It's an active area, and new surveys should settle it within a few years. Let's be clear about the limits, because there's a hard boundary here. The microwave background is a photograph of the universe at 380,000 years. Everything before that is hidden behind it, because the universe was opaque. So no light of any kind can reach us from earlier. That's not a technological limitation, it's a property of the universe. The first 380,000 years are, in light, permanently unavailable. Which means everything we say about the first minutes, the forging of the light elements, the earlier eras, the first instant, is inferred rather than observed directly. That inference is quite good. The abundances of light elements measured in old gas tell us about conditions in the first few minutes. The pattern in the microwave background carries the imprint of what happened before it was released, and the statistical properties of the fluctuations point back to inflation. But it's all indirect, and it will remain so for light. There are two possible windows onto earlier times though, and both are being pursued. One is neutrinos, which decoupled at about 1 second, and should still be present as a background, though far too low in energy to detect with any current technique. The other is gravitational waves, which decoupled essentially immediately, and which could in principle carry information from the first fraction of the first second if the B-mode signal can be found. Let's spend a chapter on that neutrino background, because it's an even older relic and it's genuinely there. Neutrinos interact so feebly that they stopped interacting with everything else about 1 second after the beginning, far earlier than photons, which had to wait 380,000 years. From that moment, they've streamed freely. And they're still here, filling space, at a density of roughly 300 per cubic centimeter, including in the room you're lying in. It's called the cosmic neutrino background, and it's an image of conditions when the universe was 1 second old. Detecting it directly is one of the great unsolved experimental problems. The energies are now so low, the neutrinos have been redshifted for 13 billion years, that no existing technique can catch them. There are proposals involving radioactive isotopes that might occasionally absorb one, and experiments in development, but nobody has done it. We know it's there indirectly. Its gravitational effect shows up in the microwave background pattern and in how structure formed. The models simply don't fit without it. Planck's data constrain the effective number of neutrino species, and the answer agrees with the 3 we know about. So there's a second, older relic bath filling the universe. We're confident it exists and we cannot see it. Detecting it would be a window onto the first second, and it may never be possible. Let's put some numbers on the radiation itself, because the proportions are surprising. There are about 410 photons from the cosmic microwave background in every cubic centimeter of space. That's a lot. Roughly 400 million per cubic meter, everywhere. And there are, on average, about 1 proton or neutron per 4 cubic meters of space, when you spread all the ordinary matter in the universe out evenly. So photons outnumber ordinary matter particles by roughly 1 billion to 1. The universe is overwhelmingly a bath of radiation, sparsely contaminated with matter. That ratio is one of the fundamental numbers of cosmology, and it carries a clue. In the very early universe, matter and antimatter were produced in nearly equal quantities, and they annihilated when they met, producing photons. If the quantities had been exactly equal, everything would have annihilated, and the universe would contain radiation and essentially nothing else. The fact that any matter survives means there was a slight excess, roughly 1 extra matter particle per billion pairs. Everything else annihilated, and the photons we now measure are largely the residue of that annihilation. So, the photon to baryon ratio is a direct measure of the asymmetry, 1 part in 1 billion, in favor of matter. Why that asymmetry exists is unknown. It's one of the major open problems in physics, and the number is written into the sky. Here's a check on the whole picture that I find rather elegant. The theory says the microwave background was hotter in the past, in direct proportion to how much the universe has expanded since. At a redshift of 2, it should have been 3 times its present temperature. At a redshift of 3, 4 times, and so on. That's a firm prediction, and it can be tested, using the same technique Michaela stumbled onto in 1941. Molecules in distant gas clouds are excited by the ambient radiation, and the ratio between molecules in different states reveals the temperature. Observe a suitable gas cloud in front of a distant quasar, measure the ratio, and you get the temperature of the microwave background at that cloud's epoch. The measurements have been done out to redshifts of 3 and beyond, and the results match the prediction. The background really was hotter in the past by exactly the right factor. There's a second method using the Sunyaev-Zeldovich effect in distant galaxy clusters, which is sensitive to the background temperature at the cluster's redshift, and it agrees. That's a strong test. A universe that wasn't expanding, or whose expansion history differed, would not produce that scaling. So we haven't only measured the temperature today, we've measured it at several points across billions of years, and confirmed that it has been cooling exactly as expansion requires. There's a frontier in this subject that hasn't been reached, and it's worth a chapter because it may open next. The microwave background is a nearly perfect blackbody, but not exactly perfect in principle. Any process that injected energy into the plasma before recombination would have left a small deviation from the ideal curve. Two kinds of deviation are possible, and they encode different eras. If energy was injected very early, before about 2 months after the beginning, the plasma could redistribute it and restore a blackbody shape, but at a shifted effective temperature, leaving a particular kind of distortion. If it was injected later, the plasma couldn't fully restore equilibrium, leaving a different signature. So measuring those distortions would probe the era between the first few weeks and recombination, a period we currently have essentially no direct information about. Possible sources include the decay of hypothetical particles, the evaporation of primordial black holes, and, most interestingly, the ordinary damping of small-scale sound waves, which is guaranteed to have happened and produces a distortion at a calculable level. That guaranteed signal is small, about 1 part in 100 million, well below what has been measured. The best limits come from COBE's spectrum instrument, and they haven't been improved since 1996. Proposals for a dedicated mission exist and have been under discussion for years. If one flies, it would open a genuinely new window, and the guaranteed signal means it would find something. Let's spend a chapter on what's coming, because several projects will report within a decade. In the Atacama Desert in Chile, at 5,000 meters where the air is exceptionally dry, a new observatory is being commissioned with tens of thousands of detectors across several telescopes. Its primary targets are polarization, the B-mode search, and gravitational lensing. At the South Pole, existing telescopes continue to observe the same patch of sky year after year, accumulating sensitivity. The polar site offers months of continuous darkness and extremely stable dry conditions. A more ambitious ground-based project is being planned, combining large numbers of telescopes at both sites, with several 100,000 detectors, an order of magnitude beyond anything currently operating. And a satellite mission is in preparation, designed specifically for large-scale polarization, which is where the primordial gravitational wave signal would be strongest, and where the atmosphere makes ground-based work hardest. Between them, the limits on the primordial B-mode signal should improve by roughly an order of magnitude, which means that within perhaps 10 to 15 years, either the signal will be found, confirming inflation and measuring its energy scale, or the limits will exclude the simplest models entirely. Either outcome would be significant, and both are worth the effort. Something worth knowing: this is not an exotic signal requiring a satellite. It's detectable with modest equipment. The original detection used a horn antenna and a cooled receiver, sophisticated for 1964, but not beyond a well-equipped workshop today. Amateur radio astronomers have detected it. The standard approach uses a satellite television dish and a low-noise receiver, comparing the sky against a reference load at a known temperature, the same basic technique Penzias and Wilson used. You can't measure the tiny variations that way, of course. Those require satellites and years of integration. But the existence of the background, an excess signal of a few degrees, the same in every direction, is within reach of a determined enthusiast with a dish and patience. There's also the older, cruder demonstration we opened with, the untuned television. That's largely a historical curiosity now, since digital broadcasting doesn't produce the same static, but it was true for decades. I mention it because it changes the character of the subject. This isn't a signal glimpsed at the edge of what's possible. It's a strong, pervasive, easily confirmed feature of the sky, present everywhere, which anyone with the right equipment can verify. The difficulty was never detecting it. The difficulty was recognizing what it was. Let's take a chapter on a consequence of the cooling that I find quietly striking. The background has been cooling since it was released, from 3,000 degrees down to 2.7, which means it passed through every temperature in between. There was a period when the ambient temperature of the entire universe everywhere was that of boiling water, and a period when it was the temperature of a warm afternoon. That comfortable era happened a few million years after the beginning, and lasted for a few million years as the cooling continued. And there was nothing there. No stars had formed. The first wouldn't appear for another 100 million years or more. No planets, no surfaces, no chemistry beyond the simplest molecules. Just a thin fog of hydrogen and helium, drifting in the dark, at exactly the temperature you'd choose for a room. The whole universe, uniformly mild, uniformly dark, and entirely empty of anything that could notice. Some writers have speculated about whether that period could have supported life somewhere, if any dense object existed to sit on, the idea being that a rocky body would have been kept warm by the background alone, without needing a star. It's almost certainly moot, since there were no rocky bodies and no heavy elements to make them from. But the fact itself is real and rather lovely. A few million years early on, when everywhere in the universe was room temperature and pitch dark. Let's follow the microwave background forward in time, because it doesn't last. It cools as the universe expands, and the universe is expanding at an accelerating rate. So the cooling continues and accelerates. In 100 billion years, the temperature will be a small fraction of what it is now. In a trillion, less still. The wavelengths stretch, the photons dilute, and the signal becomes progressively harder to detect. At some point, it becomes undetectable by any conceivable instrument. Estimates vary, depending on assumptions, but the general picture is that within a few 100 billion years, perhaps sooner, no technology could find it. Which means the evidence we've spent tonight discussing is temporary. An astronomer living in 100 billion years would have no microwave background to measure. They would also have no other galaxies to observe, since the accelerating expansion will have carried everything beyond our local group past the horizon. So they would see their own galaxy, the merged remnant of ours and Andromeda, and nothing else. No redshifts, no ancient light, no evidence of expansion or of a beginning. They would conclude, quite reasonably, that the universe consists of a single island of stars in an unchanging void. Every observation available to them would support it, and there would be no way for them to find out otherwise. That deserves a chapter of its own, because it says something about when we're alive. Everything we know about the universe's history depends on evidence that is fading. The microwave background is stretching toward undetectability. Other galaxies are receding and reddening. The cosmic web is being pulled apart. So we're living during a window in which the history of the universe is legible from the inside. That window opened when the universe became transparent, and it will close over the coming hundreds of billions of years. Later observers, doing everything right, being as careful and clever as anyone has ever been, would have access to none of this. Not through any failing of theirs, the information will simply be gone. Which makes our era unusual in a specific way. Not that we're special, that the universe is currently in a phase where its own past is recoverable. And it prompts a question worth carrying. What has already gone? What could have been measured 10 billion years ago that can't be now? 13.8 billion years in, on a small planet, a species that has had radio receivers for a century happens to be looking during the period when looking still works. Nobody arranged that. It's simply where and when we are. And it's why the map of the oldest light, made in the last 30 years, is one of the more remarkable objects our species has produced. Let's spend a chapter on the human side, because the work spanned generations. Gamow, Alpha, and Hermann predicted it in the 1940s and were largely ignored, and two of them spent decades pointing that out with justification. Penzias and Wilson found it by accident in 1964, while trying to characterize noise, spent a year eliminating pigeons and every other explanation, and shared a Nobel Prize in 1978. Dickey, Peebles, Roll and Wilkinson were weeks away from finding it deliberately, and instead explained what the other group had found. Peebles received a Nobel Prize in 2019 for his broader theoretical work, 54 years later. John Mather and George Smoot led the two COBE instruments, one measuring the spectrum, one the variations, and shared the Nobel Prize in 2006. And behind those names are thousands of others. The engineers who built cryogenic receivers, the analysts who developed foreground separation methods, The graduate students who spent years characterizing a single detector, the crews who wintered over at the South Pole to keep telescopes running through months of darkness. The result is a map of the sky, as it was 13.8 billion years ago, accurate to millionths of a degree, from which the age and composition of the universe can be read. That took about 60 years, several generations, and a great deal of very unglamorous care. Let's be honest about the gaps, because several remain. We don't know what dark matter is, though the microwave background measures precisely how much there is. We don't know what dark energy is, though the same data require it. We don't know why the expansion rate measured locally disagrees with the value the microwave background implies, and the disagreement is now hard to dismiss. We don't know whether inflation happened, in the sense of having decisive evidence. The pattern fits, but the primordial gravitational wave signal that would confirm it hasn't been found. We don't know why the primordial fluctuations have the amplitude they do. The 1 part in 100,000 is measured, not explained. We don't know why matter slightly outnumbered antimatter by 1 part in a billion, though the photon-to-baryon ratio measures it. And we don't know whether the large-scale anomalies mean anything, and given cosmic variance, we may never. What we do know is remarkably solid. The age, the composition, the geometry, the statistical properties of the initial conditions, and the fact that the universe was once a hot uniform plasma. That framework fits an enormous body of independent evidence. It's the interpretation underneath it that remains open. Let's take stock, gently, before we start winding down. The measurement is about as secure as anything in astronomy. A bath of radiation fills all of space, at 2.725 degrees above absolute zero, with the most perfect thermal spectrum ever measured, uniform in every direction to 1 part in 100,000. Its origin is understood. The moment the universe cooled enough for atoms to form, 380,000 years after the beginning, and the light was released. Its faint variations are the seeds of all structure, and their statistical properties match what a brief episode of rapid expansion in the first instant would produce. And from the pattern of those variations, 6 numbers describe the entire observable universe, its age, its contents, its geometry, and the character of its initial conditions. And those 6 numbers then predict a great deal else correctly, without further adjustment. 2 of the 6 describe substances nobody can identify. One of them is in tension with a local measurement, and nobody knows why. So the honest answer to tonight's question is, the cosmic microwave background is the oldest light there is, released when the universe became transparent, still arriving from every direction, and it has told us more about the universe than any other observation, while leaving the deepest questions exactly where it found them. There's a problem hidden in the uniformity, and it's the reason inflation was invented. Let's take it slowly. The microwave background is the same temperature in every direction to 1 part in 100,000, which sounds like tidiness and is actually deeply strange. Consider 2 patches of sky in opposite directions. The light from each has been traveling toward us for 13.8 billion years. So they're separated from each other by an enormous distance, and in the standard picture, they were never in contact. For 2 regions to have the same temperature, they normally have to exchange heat, which requires something to travel between them. But nothing can travel faster than light, and there simply wasn't time for anything to cross between those regions before the light was released. So they had no way to equalize, and yet they match to 5 decimal places. It's as though you found 2 cups of tea at opposite ends of a house, at exactly the same temperature, having never been near each other or shared a kettle. That's the horizon problem, and it was recognized in the 1960s. The uniformity that makes the microwave background so clean is precisely what makes it puzzling. There's a second problem, and it's equally awkward. The measurements say space is flat to within a fraction of a percent, which sounds like a clean result, and is actually a very strange coincidence. The reason is that flatness is unstable. In an expanding universe governed by general relativity, any small departure from perfect flatness grows over time. If the universe started slightly curved, it becomes rapidly more curved as it expands. So for it to be flat to a fraction of a percent today, after 13.8 billion years of that amplification, it must have been flat to something like 1 part in 10 to the 60th in the earliest moments. That's not a mild coincidence. It's a fine-tuning so extreme that it demands an explanation. That's the flatness problem. And there was a third. Certain theories of particle physics predicted that enormous numbers of exotic heavy particles should have been produced in the early universe, and none has ever been found. 3 separate puzzles, all about the initial conditions, all unexplained in the 1970s. And then one idea solved all 3 at once. In late 1979, a young physicist named Alan Guth, at the end of a series of temporary positions and unsure whether he'd have a career, was thinking about the missing exotic particles. He found that if the very early universe went through a brief period of exponential expansion, the particles would be diluted to undetectable levels. That solved the third problem. Then he realized the same mechanism solved the other 2. The horizon problem dissolves because the regions that seem never to have been in contact were in contact, packed together in a tiny volume, sharing heat thoroughly, before being flung enormously far apart, faster than light could follow. They match because they were once neighbors. The flatness problem dissolves because stretching any surface enormously makes it look flat locally. However, it started. The way a wrinkled sheet, pulled to the size of a continent, would appear perfectly smooth in any small patch. 1 mechanism, 3 problems, none of which it was designed to address beyond the first. And then it made a prediction nobody had asked for. Quantum fluctuations stretched to enormous scales, frozen as density variations, with a specific statistical character. Which is what the satellites measured, decades later, and found to match, including the slight tilt. Here's a detail that puzzles people who look closely, and the resolution is rather beautiful. Hydrogen atoms are ionized by photons with more than about 13.6 electron volts of energy. In temperature terms, that corresponds to roughly 150,000 degrees. So you'd expect atoms to form once the universe cooled below that. But recombination happened at about 3,000 degrees, 50 times cooler. The reason is the photon to baryon ratio we discussed. There are about 1 billion photons for every proton. A black body at a given temperature has most of its photons around a characteristic energy, but a small tail extending to much higher energies. And when photons outnumber atoms by 1 billion to 1, even a tiny fraction in that high energy tail is enough to keep everything ionized. So the universe had to cool far below the naive threshold before the number of ionizing photons dropped low enough for atoms to survive. That's why recombination waited until 3,000 degrees, and why it happened at 380,000 years rather than much earlier. And it means the timing of the oldest light in the universe is set by the matter-antimatter asymmetry, by the fact that 1 particle in 1 billion survived annihilation. Change that number and the photograph would have been taken at a different moment. Something worth clarifying, because the phrase surface of last scattering is slightly misleading. Recombination wasn't instantaneous. It took several tens of thousands of years for the ionization to drop and for photons to stop scattering. So the light we receive wasn't all emitted at exactly the same instant. Different photons had their final scattering at slightly different times, spread across that window. Which means the surface has thickness. It's not a wall, but a layer, a fog bank, with the last scattering happening throughout it, rather than at a sharp boundary. That thickness has a consequence. It blurs the pattern slightly. Very small features get washed out, because photons emerging from different depths within the layer carry slightly different information and get mixed together. There's a second blurring effect too. Photons diffusing through the plasma before release could travel a certain distance, and that diffusion smooths out density variations smaller than a particular scale. A process named after Joseph Silk, who worked it out in 1968. Both effects show up in the power spectrum as a decline at small angular scales, the damping tail, where the peaks get progressively weaker and eventually disappear. And that tail is informative in its own right. Its shape depends on the composition of the plasma and on the helium abundance, and measuring it provides another independent check on the model. Here's a connection that ties tonight's subject to the arrangement of galaxies, and it's one of the most satisfying results in cosmology. Those sound waves in the early plasma froze when the light escaped. Each initial overdensity had sent out a spherical shell of compressed matter, and that shell stopped expanding at a particular radius. The dark matter stayed concentrated at the center. The ordinary matter was left in a shell around it, and galaxies later formed preferentially in denser regions, both at the centers and on those shells. Which means that even today, if you pick any galaxy and ask how far away its neighbors are, there should be a very slight excess at that particular separation, around 490 million light-years in today's stretched units. It's a faint signal, a rise of about 1% above the smooth background. But survey enough galaxies, and it emerges clearly. It was first detected in 2005, and it's been measured with increasing precision ever since, out to great distances. So the same acoustic oscillations appear twice, as peaks in the microwave background power spectrum and as a preferred separation between galaxies today. Two completely different observations of the same physical phenomenon, separated by 13 billion years. And they agree. That preferred separation has a use, and it's become one of cosmology's most important tools. Because the physical size of those frozen shells is calculable from the microwave background, we know their true dimensions, which makes them a standard ruler, an object of known size, visible at many different distances, and therefore at many different epochs. Measure how large that scale appears at various redshifts, and you can chart how the expansion has behaved across billions of years. Without exploding stars, without standard candles, without any of the calibration ladder those methods require. That's what the large galaxy surveys are doing, mapping millions of galaxies in 3 dimensions, extracting the acoustic scale at each epoch, and tracing the expansion history. And it works. The results agree with the supernova measurements and with the microwave background, and together they pin down the model far better than any one method could. They also constrain dark energy directly by measuring whether its influence has changed over time, which is where the recent hints of possible evolution have come from. So the sound waves that rang through the early universe, whose final instant is frozen in the microwave sky, have become a measuring tape stretched across cosmic history. That's a remarkable amount of use to get from one phenomenon. There's a measurement the microwave background makes that has nothing obviously to do with cosmology, and it's rather remarkable. Neutrinos have mass. We know that because they change type as they travel, which is only possible for particles with mass, a discovery that won a Nobel Prize in 2015. But the masses are tiny, and laboratory experiments can only place upper limits. Measuring them directly remains one of the great outstanding challenges in particle physics. Cosmology can help. Neutrinos are abundant, 300 per cubic centimeter everywhere, and if they have mass, they contribute to the total matter content. But because they move fast, they stream out of small structures rather than falling into them, suppressing the growth of structure on small scales by a calculable amount. So by measuring how much structure exists today, and comparing with what the microwave background says the initial conditions were, the total neutrino mass can be constrained. The current limits from cosmology are tighter than anything a laboratory has achieved, placing the sum of the 3 masses below a small fraction of an electron volt. Which means one of the most stringent measurements of a fundamental particle property comes not from an accelerator, but from a map of the sky combined with a survey of galaxies. Here's another quantity the microwave background measures indirectly, and it reaches back to the first few minutes. In those minutes, the universe was hot and dense enough to fuse protons and neutrons into light nuclei, producing hydrogen, a great deal of helium at about a quarter of the mass, and traces of deuterium and lithium. How much of each depends sensitively on how densely packed the protons and neutrons were. Now, the helium abundance also affects the microwave background, Helium recombines earlier than hydrogen, which changes the free electron density during the era when the acoustic oscillations were being imprinted, leaving a subtle signature in the damping tail of the power spectrum. So the microwave background can measure the primordial helium abundance independently, and the answer agrees with what's measured directly in the spectra of metal-poor gas clouds, which is a satisfying consistency. Nuclear physics from the first 3 minutes, checked by radiation, released 380,000 years later, and by observations of gas clouds billions of years after that. 3 independent windows onto the same era, all agreeing. Let's spend a chapter on the practicalities, because measuring temperature differences of a few millionths of a degree is not straightforward. The fundamental difficulty is stability. If a detector's own temperature drifts by a millionth of a degree, the signal is swamped. The solution is differential measurement. Rather than measuring the absolute temperature of a patch of sky, instruments compare 2 patches, or compare a patch against an internal reference, and record only the difference. Drifts affect both equally and cancel. Then the instrument scans, sweeping across the sky in a pattern designed so that each patch is compared against many others at many times and orientations. From millions of such comparisons, a map is reconstructed, solving a large system of equations to find the temperature pattern consistent with all the differences. The detectors themselves are extraordinary. Modern instruments use bolometers, tiny absorbers cooled to a fraction of a degree above absolute zero, whose electrical resistance changes measurably when they absorb a handful of photons. Planck's detectors operated at 1/10 of a degree above absolute zero, which made them, for a period, among the coldest known objects in space. There's a reason satellites were built for this, and it comes down to water vapor. Water in the atmosphere absorbs and emits at microwave wavelengths, exactly the band the cosmic background occupies. So the sky itself glows, and that glow varies with weather, humidity, and elevation. From sea level, atmospheric emission overwhelms the signal completely. So ground-based work requires the driest, highest sites available. 2 stand out. The Atacama Desert in Chile at 5,000 meters, where it essentially never rains, and the South Pole at nearly 3,000 meters of elevation on the ice, where the extreme cold means the air holds almost no moisture, and where the sun doesn't rise for months. Both host major telescopes, and both produce excellent data, particularly at small angular scales, where large ground-based dishes outperform satellites. But for the largest scales, and for full sky coverage, space is necessary. Above the atmosphere, there's no emission and no absorption, and an instrument can observe the entire sky rather than the fraction visible from one location. The satellites were placed at a gravitational balance point, about 1.5 million kilometers away, on the side facing away from the sun, which lets a single shield block the sun, Earth and Moon at once, keeping the instrument permanently in shadow. Between the ground and space, there's a third approach, and it produced one of the key results. A balloon can carry an instrument to about 40 kilometers, above 99% of the atmosphere. Not as good as space, but far cheaper and much faster to build. In the late 1990s and early 2000s, several balloon experiments flew, and one in particular changed things. It flew over Antarctica, carried by the circumpolar winds that blow in a loop around the continent during the austral summer, allowing a flight of about 10 days that returned the payload close to where it started. Its results, released in 2000, measured the first acoustic peak clearly for the first time, and established that space is flat several years before the satellites confirmed it with greater precision. That was the moment the geometry question was settled, and it came from an instrument hanging under a balloon over the ice. Balloon flights continue, testing detector technologies and observing at frequencies difficult from the ground. There's something appealingly modest about it. One of the most important measurements in cosmology came from equipment that spent 10 days drifting over Antarctica and then parachuted onto the ice to be collected. Let's do something visual for a chapter, because it's a pleasant thing to picture. Suppose your eyes were sensitive to microwaves at the relevant wavelengths, with enough precision to see the variations. The first thing you'd notice is that the sky would not be dark. It would glow everywhere, uniformly. No gaps, no black between the stars. The entire sky would be a featureless field of faint light. Stars would barely register. They emit almost nothing at those wavelengths compared to their visible output. Galaxies would be faint. What would dominate is the band of our own galaxy, glowing across the middle from dust and from electrons spiraling in magnetic fields, brighter than the background itself, which is why it has to be masked out of every map. And if you could subtract that and see the variations, you'd see soft mottled patches, a degree or so across, differing by millionths of a degree, spread evenly in every direction. None of it would line up with anything visible. The patches are the seeds of structures that formed long afterwards, and everything has moved and grown enormously since. That's worth extending, because the sky looks different in every band, and each shows a different universe. In radio, it's dominated by our galaxy's synchrotron glow, and by distant active galaxies, jets and lobes from feeding black holes, some of them enormous. In microwaves, it's the cosmic background, plus the galaxy's dust. In infrared, it's warm dust, star-forming regions glowing where visible light cannot escape. In visible light, it's stars, which is a narrow and unrepresentative window that we happen to have evolved to use. In ultraviolet, it's hot young stars. In X-rays, it's gas at millions of degrees in galaxy clusters, and material falling onto neutron stars and black holes. In gamma rays, it's pulsars, active galaxies, and bursts from collapsing stars. 7 different skies, all present at once, showing entirely different things. And for almost all of human history, we could see exactly one of them. The cosmic microwave background lives in a band we've only been able to observe for about 75 years, which is a good measure of how recently this entire picture became available at all. Let's spend one more chapter on the central diagram, because knowing how to read it makes the whole subject clearer. Along the bottom is angular scale, running from large patches on the left to small ones on the right. Up the side is how much temperature variation there is at each scale. The curve rises from the left, reaches a tall first peak at about 1 degree, twice the width of the full moon, then dips, rises to a second peak at about half that scale, dips again, rises to a third, and continues with progressively smaller peaks that fade away at the smallest scales. That's the whole thing. Everything cosmology claims to know about the contents and geometry of the universe is extracted from the positions and heights of those bumps. The position of the first peak gives the geometry. The ratio of the odd to even peaks gives the ordinary matter density. The third peak's height gives the dark matter density. The overall tilt of the curve gives the character of the primordial fluctuations. The decline at small scales gives the damping physics and the helium abundance. And the fit is astonishing. 6 parameters, adjusted to match, reproduce thousands of independent measurements across the whole curve with no significant residuals. When that plot is shown with the data points and the model curve overlaid, the points sit on the line so precisely that you have to look carefully to see that there are data at all. A chapter on motivation, because the effort involved is enormous. The immediate reason is that this is the only direct observation we have of the universe before stars existed. Everything else in astronomy studies objects that formed later. This studies the conditions they formed from. The second reason is precision, because the physics of that era is simple: a hot uniform plasma, well described by known equations, with no complicated astrophysics. The measurements can be interpreted cleanly. Galaxies are messy. The early plasma is not. That's why cosmology became a precision science through this route, rather than through studying galaxies. The third reason is that it constrains fundamental physics. Neutrino masses, the number of particle species, the nature of dark matter, the energy scale of inflation, all are probed by this radiation, at energies and epochs no laboratory can approach. And the fourth is that it's the only place where a quantum gravitational effect might be observable. If primordial gravitational waves are found in the polarization, that would be the first evidence of quantum fluctuations of space-time itself. So the effort is justified several times over, which is why substantial resources go into instruments, observing from Antarctica, the Atacama, and space. Let's be careful about one thing, because the microwave background is sometimes described as explaining the beginning, and it doesn't. It shows us the universe at 380,000 years, in a state that was already hot, already expanding, already filled with matter and radiation in specific proportions, and already carrying density variations of a specific amplitude. It tells us what the conditions were. It doesn't tell us why they were those conditions. Why is there matter rather than nothing? Why did matter slightly outnumber antimatter? Why do the fluctuations have the amplitude they do? Why is there dark matter, and what is it? Why does empty space have the energy it apparently has? None of those is answered by this radiation. They're measured by it, precisely, and left standing. And the deepest question, why there is a universe at all, or what if anything preceded the hot dense phase, is entirely untouched. The microwave background is a photograph of a moment. It says nothing about how the camera came to exist, which is worth saying plainly. This is the most informative observation in cosmology, and it answers the how questions superbly, and the why questions not at all. That's not a criticism. It's simply the shape of what an observation can do. Let me tell the story of a single photon, because it makes the whole thing concrete. It came into existence somewhere in the hot plasma, long before the moment we've been discussing, created and destroyed and recreated countless times as the material absorbed and emitted it. For hundreds of thousands of years it went nowhere. Every fraction of a second it collided with a free electron and was flung off in a random direction, then again and again, making no progress at all. Then, at about 380,000 years, an electron it was heading toward was captured by a proton, and it passed by without interacting. And it kept going. Nothing was in its way anymore. It traveled in a straight line through the expanding darkness of the cosmic dark ages, while the gas around it slowly gathered into structures. It passed through the region where the first stars would ignite 100 million years later, and it was long gone by then. It passed through space, where galaxies would assemble, and where clusters would form, being bent very slightly by their gravity in passing. It stretched the whole time, its wavelength growing with the expansion of space, from visible orange down through infrared, cooling by a factor of 1100. And a moment ago, after 13.8 billion years, it arrived at the roof above you, or the wall, or your skin, and was absorbed. That was the second interaction of its existence, and the last. Let's spend a chapter on what happened next, because the microwave background is the last light for a long time. Once released, the radiation kept cooling, and within a few million years it had faded from visible orange through red and into the infrared, below anything an eye could register. And there was nothing else. No stars had formed, no galaxies. The universe contained hydrogen, helium, a trace of lithium, dark matter, and the fading glow. That period is called the Cosmic Dark Ages, and it lasted somewhere between 100 and 200 million years. A genuinely dark universe, full of material, with nothing shining anywhere. During it, gas drifted slowly into the gravitational wells that dark matter had prepared, cooling by a trace of molecular hydrogen, until finally some region collapsed far enough to ignite. The first stars. And then, over the following hundreds of millions of years, enough of them to matter, carving out bubbles of ionized gas in the neutral fog, which grew and merged until the whole universe was transparent to ultraviolet light again. That process, reionization, left its own mark on the microwave background. Free electrons scatter photons, so a fraction of the ancient light was scattered on its way here. Measuring that fraction gives an independent estimate of when the first stars appeared, and it's one of the 6 parameters in the Standard Model. There's a conceptual point worth a chapter, because it sounds like a contradiction and isn't. Relativity says there's no absolute rest, no preferred frame against which all motion can be measured. That's foundational and thoroughly tested. So how can we say we're moving at 370 kilometers per second? The answer is that the microwave background provides a preferred frame without being an absolute one. It's the frame in which the radiation appears uniform. And because it was released everywhere at once, from material that was very nearly at rest relative to itself, that frame is essentially the same everywhere in the universe. It's the frame in which the universe as a whole looks isotropic. That doesn't violate relativity, because it's defined by the contents of the universe rather than by space itself. The laws of physics remain identical in every frame. One frame simply happens to be picked out by what's in it. The analogy sometimes used is a still room full of air. There's no absolute rest, but there's an obvious reference, the frame in which the air isn't moving, and you can meaningfully state your speed relative to it. So our motion is real and measurable, and it's motion relative to the average matter of the universe. And that's the only sense in which the number means anything. There's an unresolved anomaly connected to that, and honesty requires a chapter. The standard interpretation is that the dipole is entirely kinematic, caused by our motion, full stop. But there's a way to check. If it's due to our motion, the same motion should produce a matching dipole in the distribution of distant objects, because sources ahead of us appear slightly brighter and slightly more numerous. That effect is predictable in size, and it's been looked for in catalogues of distant radio galaxies and quasars. Several studies have found a dipole in those catalogues pointing in roughly the right direction, but larger than the microwave dipole predicts, in some analysis by a factor of 2. If that holds, it would mean either that the microwave dipole isn't entirely due to motion, or that the distant universe isn't as uniform as the standard assumptions require. Both would be significant. The measurements are difficult, with real concerns about how catalogues are assembled and how incomplete sky coverage affects the result, and not everyone is convinced. So it's an unresolved anomaly rather than an established finding, but it touches one of the foundational assumptions, and it's being actively examined with better data. A chapter on a technical difficulty, because it explains why one satellite instrument was designed the way it was. Measuring temperature differences across the sky is comparatively straightforward, using the differential technique we discussed. Measuring the absolute temperature and confirming the spectrum is a perfect blackbody is much harder, because you need an accurate reference to compare against. The solution was to carry one. COBE's spectrum instrument included a precisely constructed internal blackbody, whose temperature could be controlled and known exactly, and the instrument alternated between viewing the sky and viewing the reference. When the two matched, the difference signal went to 0, and the reference temperature at that point was the sky temperature. That's why the result was so clean. It wasn't a model-dependent inference. It was a direct comparison against a known standard carried into orbit. The instrument achieved a precision that has not been surpassed in the 30-odd years since. Any future improvement on the spectrum would require a new dedicated mission, and that's exactly what the spectral distortion proposals we discussed would provide. Which is a nice illustration of how measurement actually works. To find out how hot the universe is, someone built a small, perfect furnace, took it to space, and compared. A short chapter on the map as a cultural object, because it has an unusual public life. The mottled oval has appeared on magazine covers, in documentaries, in textbooks, on posters, and on the walls of physics departments everywhere. It is probably the most widely reproduced scientific image of the past 30 years, alongside the deep field photographs. Part of its appeal is aesthetic. It's a pleasing pattern, and the color scales chosen are attractive. Part is the claim attached to it, a picture of the universe as an infant, which is a genuinely arresting thing to be able to say. And part is the 1992 announcement, which was accompanied by some memorable overstatement that lodged in public memory, and which the scientists involved spent years gently qualifying. There's a risk in that fame, which is that the image gives an impression of a chaotic, lumpy early universe. The reality, as we've discussed, is almost perfect uniformity, with variations amplified tens of thousands of times to be visible at all. But I don't begrudge it. A picture of the universe at 380,000 years old, made from measurements of millionths of a degree, hanging on office walls, that's a reasonable thing for a species to be pleased about. One last reflective chapter before the recap. If human beings had developed radio astronomy a few billion years earlier, the microwave background would have been hotter and easier to detect, perhaps 10 or 20 degrees rather than 2.7. It would have been noticed sooner and more obviously. If we develop it a few 100 billion years later, it wouldn't be detectable at all. We happen to be observing during a window where the signal is faint enough to have taken until 1964 to find by accident, and strong enough to be measured to millionths of a degree. That's not a coincidence in any deep sense. The window is enormously long, hundreds of billions of years wide, and we're comfortably inside it. But it's worth noticing that the window exists, and that it closes. The evidence for the beginning of the universe is a temporary feature of the universe. Later observers, doing everything right, would have no way to discover any of this, and earlier ones, if there were any, would have found it more easily than we did. We arrived at a reasonable time, with reasonable difficulty, and we found it by accident while trying to eliminate noise from an antenna, which is, all things considered, a rather good way for it to have happened. A short chapter on terminology, because the naming of this whole subject is a curiosity. The phrase Big Bang was coined by Fred Hoyle on BBC Radio in 1949 while explaining the competing theories. He was a defender of the steady-state model, and he was reaching for a vivid contrast. Accounts differ on whether he intended it dismissively. He later insisted he did not, that he was simply looking for an image that would land with a listening audience, and that his tone had been misread ever since. Either way, it stuck, and it's an unfortunate name, because it suggests an explosion at a location in pre-existing space. The actual picture is quite different. Not an explosion in space, but an expansion of space, happening everywhere at once, with no centre and no outside. There have been attempts to replace it. In the 1990s, a magazine ran a competition to find a better term, receiving thousands of entries, and the judges concluded that none was an improvement. So it remains, along with planetary nebulae that aren't planets, and recombination where nothing had previously combined, and type Ia supernovae that have nothing physically to do with type Ib, which is a fair summary of scientific terminology in general. Names survive on inertia, not accuracy, and every generation learns to explain them. Let me lay out the quantitative picture in one place, slowly, because it's satisfying to have it in order, and you never have to remember any of it. Temperature today, 2.725 degrees above absolute zero. Temperature at release, about 3,000 degrees. Stretching factor since about 1100. Age of the universe at release, 380,000 years. Age today, 13.8 billion years, known to better than 1%. Uniformity, the same in every direction to 1 part in 100,000, once our own motion is subtracted. Our motion, from the dipole, about 370 kilometers per second for the Sun, 630 for the local group. Photon density, about 410 per cubic centimeter, everywhere. Photon to baryon ratio, about 1 billion to 1, which measures the matter-antimatter asymmetry. Composition, from the peak structure, about 5% ordinary matter, 27% dark matter, 68% dark energy. Geometry, flat, to within a fraction of a percent. Primordial fluctuations, amplitude about 1 part in 100,000, nearly the same on all scales with a slight measured tilt, and the whole pattern, across thousands of independent measurements at every angular scale, fitted by 6 free parameters with no significant residuals. If you're still awake, let's walk back through it once more, gently, with nothing to follow and nowhere to arrive. It began with television static, the grey snow on an untuned screen, about 1% of which was light from the beginning of the universe, arriving after 13.8 billion years and appearing as a few flecks among the interference. People watched it for decades without knowing. And it's still arriving. 400 million photons per cubic meter everywhere, passing through the roof and through you. Each one having traveled undisturbed since before there were stars. And you are the first thing it has touched. Before it was released, the universe was a plasma, bare nuclei and free electrons, so densely packed that light could not travel any distance without being scattered. Bright everywhere and completely opaque. Then it cooled to about 3,000 degrees, and the electrons were captured into orbits and neutral atoms formed. And the instant that happened, there was nothing left to scatter light, and the fog lifted, and all that trapped radiation set off in straight lines and has been traveling ever since. Expansion stretched it by a factor of about 1100, from a bright orange glow down through infrared into microwaves, and cooled it in the same proportion, from 3,000 degrees to 2.7. And in 1964, 2 engineers in New Jersey found a persistent hiss they couldn't account for. They checked everything. They evicted a pair of pigeons and scrubbed out the antenna. The signal was unchanged. 40 miles away, a group at Princeton was building an instrument to look for exactly that, and had to be told they'd been scooped. Then 27 years of looking for structure in it and finding none, which was becoming a problem because the universe is lumpy now and the seeds had to be somewhere. In 1990, a satellite measured its spectrum and found the most perfect blackbody curve ever observed, anywhere, and the audience stood up and applauded a graph. In 1992, the same satellite found the variations, mottling at the level of 1 part in 100,000, spread across the whole sky. Those patches are the frozen last frame of a sound. In the early plasma, gravity pulled matter into dense regions and radiation pressure pushed back, and the whole universe rang with pressure waves for hundreds of thousands of years. Until the light escaped, the pressure vanished, and everything stopped mid-oscillation. From the harmonic content of that frozen sound, the instrument can be deduced. The first peak says space is flat. The odd and even peaks together say ordinary matter is 5%. The third says dark matter is 27%. Flatness demands 100, and so 68% is something else entirely. 6 numbers fitted to that curve reproduce the entire pattern across the sky, and then correctly predict the distribution of galaxies, the abundances of the light elements, and the growth of structure over billions of years. And underneath it all, the deepest questions remain untouched. Nobody knows what the 27% is, or what the 68% is, or why the local expansion measurement disagrees with what this light implies. Meanwhile, the light itself is fading, stretching toward undetectability on a timescale of hundreds of billions of years, after which no observer could ever discover any of it. Let me leave you with some things to rest your attention on, not to learn, just quiet facts, true right now while you lie still. Filling this room, arriving from every direction at once, are about 400 million photons per cubic meter, released when the universe became transparent, having traveled in straight lines ever since. A number of them are landing on you as you lie there, and you are the first thing they have touched in 13.8 billion years. Every one of them was, at the moment of release, part of a bright orange glow filling all of space, and each has been stretched by a factor of 1100 on the way here. 1.5 million kilometers away, on the far side of the Earth from the Sun, is the quiet spot where 3 satellites have sat in permanent shadow, mapping that light to millionths of a degree. At the South Pole, through months of continuous darkness, telescopes are observing the same patch of sky they observed last year and the year before, accumulating sensitivity, looking for a swirl in the polarization that would be the fingerprint of the first fraction of the first second. And in the Atacama Desert, 5,000 meters up in air so dry it essentially never rains, tens of thousands of detectors cooled to a fraction of a degree above, absolute zero, are doing the same. They're doing it tonight, and they'll still be doing it in the morning. So here's where we stop. Everything you have seen tonight in your mind, the fog, the moment it lifted, the sound waves frozen mid-oscillation. The mottled map comes from light that is passing through this room right now, silently, in enormous quantities, and has been all your life. It's the oldest thing there is. Nothing you will ever encounter has been traveling longer or come further, and it arrives everywhere, evenly, without any effort, from every direction at once, and it has been doing that since long before there was an Earth to arrive at. There's nothing to do about it. It requires nothing, disturbs nothing, and has no effect on anything in this room except that it is here. Let your breathing get slower. You don't have to make it happen. It's already happening, on its own, the way it has all your life. Let your jaw loosen. Let your hands stay wherever they've fallen. Let the bed take your whole weight. The universe was once everywhere, a bright orange glow. It cooled through comfortable temperatures a few million years in, with nothing present to notice. And it has gone on cooling ever since. And tonight, it stands at 2.7 degrees above absolute zero everywhere, including in the space between you and the ceiling. It will still be here in the morning, a little cooler, arriving quietly, as it has for 13.8 billion years. Sleep well.